class, and then I think we are recording now. So as I tell you, we are going to start a new topic. So essentially, this topic is about interpolation. Can you see the presentation? Yep. Okay. So we're going to start with interpolation, and interpolation techniques would be actually a good subtopic to say that. So this is actually two before the last class, the last unit. So we are very close to the end of the class. So let's start. So interpolation. So in simple words, so we have to obtain a good definition of interpolation, and also why do we need interpolation? So in simple words, interpolation means estimating a value inside a data set of data points. So, but why do we use this? For example, let's imagine that Montoya has actually a ice cream company in Coatzacoalcos. So it should be actually a good deal because in Coatzacoalcos is very hot and humid. So ice cream must be a popular company. So he decided to start a company, and he started to actually analyzing the sales based on the temperature. For example, he actually has this plot because he's an engineer as well. So he says that the sales of his company in pesos, for example, per day is gonna depend on the temperature of the day. So he recorded that when the daily mean temperature was actually equal to 12, he has only 2,200 pesos of revenue. Then he recorded at 15, not 15, but almost 14 degrees. So he had a little bit more. So he started to record every day with respect to the mean temperature of the day. So in very hot days, he got even actually 600 pesos per day. And then in some days where the temperature was adequate, like 18 or between 18 and 20, so he had like a mean revenue of 400 pesos. Not bad for a small company. So he saw this, but then he saw that he doesn't have actually data between these 2 points, between 20 and 20. So he wants the sales for 21. So he said, okay, let's actually calculate the revenue for 21 Celsius degrees. But he doesn't have this value. So for that reason, he decided to, right, remember I took a class with Dr. Joseph. So now I'm actually gonna do some interpolation techniques. And I'm pretty sure that so far in your engineering life has dealt with several ways to interpolate or several data that you need to interpolate, and you use, for example, linear regression or linear interpolation. So if we actually go to internet, so you'll see that you have actually a very famous equation, linear interpolation, which let's just use the famous, no, not today. So today is not good for Wikipedia. Well, sounds like it's gonna be, okay. So, so for example, we have the linear interpolation. It's actually this formula that you have here. This is the formula. So J equal to J0 plus X minus X0 times the slope, which is J1 minus J1 minus Y0 divided by X1 minus X0. So we have the linear interpolation. We are assuming that the value between this and this actually follows a line, right? So he wants to do the linear interpolation, so he wants to do that, so we will use this equation. So we can rather use this equation, just write it down, and you'll see that if we actually go to this calculator right here, so In general, we can say that, for example, if we see the table or the plot, so for, I would say like for, this is 20, for 19.5, we have a revenue of, for, let's just call it like about 400 pesos, okay? So for 19, we have 400 pesos. And then for the second one, we see that we have, for the 22, we have a revenue of about 510 for 22. So 510, 22, 510, and then you want to calculate for 21. So, and then we calculate and we see that it's 473, or I just make the calculation visually just by a linear regression, and I said that I was about 480 pesos. So this is a linear interpolation. My question is, have you used linear interpolation before? Have you used linear interpolation before?
No, perfecto, que yo me acuerdo.
No? Okay, let's actually explain it better.
Nada más
Right?
me conozco un método de interpolación, pero pues yo supongo que lo vamos a ver, pero este lineal no.
No, so linear interpolation is actually very easy. So you see it here like
Profe, una pregunta.
Yes.
La interpolación lineal, bueno, yo creo que queda explícito en el título, pero solamente aplica para funciones que son una recta, no aplica para curvas.
Ok. Aplica, no, interpolación lineal solamente aplica cuando tú defines que el valor que estás buscando está entre dos puntos y la variación de ese punto al otro
es una línea. Ah,
Exacto.
ok, perfecto. Ok. Gracias, que tenía esa duda ahorita que vi el dibujito que está aquí presente en la pantalla. Ok.
Exactly. So that's what I'm going to do. So let's actually take this a little bit further. Let's take it to Excel. So let's take it to Excel and then we'll see something more specific. So in general, I think that, well, this is not that good, but let's do our best. So let's actually take this one to, whoa, thank you, Excel. So let's take this one to this plot. So capture on C, and then let's take it to a black one of this one here. So let's take also the one we have here. And then the values. So we're talking about the values of the values that we use in this example, in this calculator. So we use 19, and then we use 400, we use 21, and we use 22, and then 410. So I'm going to increase the font because I think this is not very nice to see. Oops, not that bad. It's huge now. So as you make this one smaller, then we make this one smaller. Something like this. Okay, so let's just use, I like consolas in Excel. I think it's clearer. Oh, I don't have consolas? Really? Well, I have Georgia. So we need this value, right? So, and then let's go and take, of course, the linear interpolation formula. So we can take this formula And then I'm going to do the same. So I'm giving you some classes of how to do, also how to use Macintosh. So this is the formula, right? So then, of course, y is this one. This is y. So let's actually do something like this again. So let's just use this. So this is y. This is going to be y0. This is going to be, of course, in this case, we have, sorry. Well, this is going to be x. This is y. This is going to be x0. This is going to be y0. This is going to be y1. And this is going to be, y0. Y0. This is going to be y1. So this is the way we have actually coded this part with respect to this one. So the one that we need is this one, right? So in general, we apply this one. Yep.
En la fórmula, en la columna de la izquierda, en la última sería x1, ¿no?
Oh, yeah. So, sorry, this x1.
X1, yeah. Okay.
Yeah, thank you very much. So x1, j1. So these are the columns of x's, this is the column of y's. So there we have all the expressions, all the unknowns that we have here. So we have this one known, this one known, this one known, this one known, and this one known. So essentially, if we actually follow the formula, we say like we need y0. So y0 is this one, right? Plus parenthesis of x, this one is x, minus x0, which is this one, right? And then times this one is going to be j1 minus j0, and then this is going to be divided by x1. Oh, I think I made a mistake here, sorry. So this is not the one. So we say like we have the x, which is this one, of course, minus x0 is this one, and then we have the y1, which is this one, y1 minus y0. And now we can go to the parentheses again, and then we have x1, which is this one, minus x0. And then we just see that we have 473.333, which is actually consistent with what we did before in this exercise right here. So remember that when we use this one, the result was equal to this. So this is linear interpolation. We won't see linear interpolation because linear interpolation, it's actually one of the simplest methods you can find in general. Okay, so this is linear interpolation, and the assumption on this under this point is that the transition from this one to this one follows a linear pattern. Okay, every point that you want to actually calculate between this point and this point follow a linear pattern. So this is discussable because sometimes this is not linear, sometimes this is actually a curve. So that is why in this class, instead of just looking at this basic knowledge as linear interpolation, we are moving to a more extent and more comprehensive way to do interpolation. So this is linear interpolation, and we are moving to some more complex knowledge. Okay, but in general, this is why we need interpolation. So we can see that the points are the sample data here. This is the sample data. This is the points that you are collected from Montoya's company, of course, in this case. However, we are interested in knowing the sales. Well, the temperature was 21, and then we just used linear interpolation. Okay. we see that we do not have that information at hand, so that we need a specific equation to follow this. This, you can see that this is actually a linear pattern. But then we can also say that we can have a polynomial actually passing through all the points, right? So we can actually pass through all the points. So we'll see this in a second. So we have here, so we see that we solve this interpolation using linear expressions. And then, of course, in this class, we are going to explore some other interpolation methods. The methods that we are going to see in this class are three mainly. So the first one is going to be the Lagrange interpolation. Then we're going to use the Newton differences, or Newton divided differences, they call it. And then it's spline. And the splines, we are going to be only the more complex splines, which is the third term or third degree splines. Okay, so that's what we're going to see. Today, we're going to focus mainly in Lagrange interpolation and Newton divided differences. Okay, so let's just go to interpolation. So a function is to interpolate a set of data points. The data points, of course, are these points, this one, and this one, such as 0.1, 2 times 2, and then 2, 3, 4. Sorry, 3, 4 here. So of course there is a parabola that passes through the 3 points and is as seen in this picture. This parabola actually is called the degree 2 interpolating polynomial. So you see that you have a polynomial here that is degree 2 and passes through these points. So what does it tell us about this? So we have 3 points, but then this is not a third order polynomial. So this is a 2-degree polynomial or degree 2 polynomial. So in this case, you see that there is a rule, a kind of rule, that you will find always a polynomial of degree n-1, which n is equal to the numbers of points passing through all the data set. Okay, so if you have 3 points, you will have a second degree polynomial. If you have 4 points, you will have a third degree polynomial. If you have 5 points, you're going to have a 4th degree polynomial. If you have 6 points, you're going to have a 5th degree polynomial. So is that clear? Is it that clear?
O sea que entre más puntos, más grande va a ser el polinomio.
Yes, but it always is going to be n-1 degree.
Sí, uno menos.
Exactly.
Okay.
Exactly. So that's something to keep in mind. Not always, but in general. That's a kind of a rule to actually define a degree of the polynomial passing through several points. But it's not always true. We'll see this in this class. Okay, so the definition, the function y equal to px, which is a polynomial, interpolates the data points x1, j1, all the way up to xn, comma, yn, if p xi is equal to yi, for each i's from 1 all the way to n. Okay, that would be the definition of interpolation. So we are just going to actually create a polynomial passing through the data sets from this value equal to 1 to x equal to 1. And also, of course, as I tell you, you're always going to have 1 degree less in this case. So we can make some observations about these claims. So the first one is P is required to be a function. Of course, this is going to be a function. The x values have to be all distinct. So we cannot have same values of x. There is no restriction in y. So we can have same values of y, but we cannot have same values of x. So when I see this, so for example, if we go back to this one, so this is the value of x. This is 0, this is 2, this is 3. So they are all different. In this case, if I have 0 here and 0 here, so this is not possible because we always have to have increasing numbers in X. So 0, 2, 3, or 0, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, but never we are going to have a same value of X. They all have to be distinct. And of course, there is no restriction in the value of Y. Okay, so we are only using polynomials to interpolate. And the last point would be a question. Is there always a polynomial to actually interpolate all the points? So as I said, if all x's are distinct, the answer would be yes. No matter how many points are given, there is some polynomial y equal to px that runs through all the points. But one good question would be, Professor, why do we use polynomials? So if you remember, at the very beginning of the class, we actually did one problem. I gave you a problem with MATLAB, that a function that was called nest. And we did nested multiplication. So, ¿se acuerdan cómo evaluamos un polinomio múltiples veces a través de un programa que se llamaba nest? Que era prácticamente como pensar como una computadora o minimizarle el número de pasos que yo tenía que hacer para evaluar un polinomio. Fue lo primero que vimos en la clase. Y les dije, cuando lleguemos a Interpolation, lo vamos a volver a ver.
Sí, profe, que era más o menos como factorizar, ¿no?
Exactamente. That's the one. So we're using polynomials. Why? Because they're actually very, very easy to handle. They are straightforward mathematical, and they have straightforward mathematical properties, so that they are very, very useful. In general, for example, more complex methods such as finite different elements, well, not finite, even differences, finite differences, we will see actually finite differences, finite element and volume element methods use polynomials to interpolate between points. Why? Because they are easy to handle. So that's why we're using polynomial, because they are easy entities. Okay, so that's one of the observations. So I would like to actually show you, before we start into Lagrange interpolation, for example, I'm going to show you something in MATLAB. So to give you an idea of that, there is always a polynomial or a function to actually interpolate. So let MATLAB actually open. So give it a second. So let's give it a second and we will see. We will see. So this is the program I was about to show you. So in MATLAB, this is a software I have. So in MATLAB, for example, we can actually run it. And then I got actually a Cartesian plane, right? Or an Eulerian plane. So if I actually show you this, so we'll see that if I have 1 point, 2 points, I have a linear interpolation. But I have another point here, and there is always a polynomial here that is actually interpolating. So I add on 1 point, there is another one. I add 1 point, there is another one. I add another point, there is another one. Another point, there would be another one. One more point, one more point, one more point, one more point, and so on and so on. So there will be always, if you think about it, actually this go all the way down here. So you can probably don't see where it actually converges, but in general, there is always a polynomial that we can calculate that will pass through all these points that I have. So this would be actually the perfect interpolation because they passes through all the points. Okay. So this is one example of one code that we actually can make in MATLAB to simulate or to at least have an idea of what I'm talking about. Okay. So that would be it so far. So in general, that's what I wanted to show you. Let's continue with the class. So the first method that we are going to discuss is actually what we call the Lagrange interpolation. So the Lagrange interpolation, we can start by assuming that n data points, in this case x1, y1, all the way down to, all the way up to xn, yn are given. So we have a data set. How many points? Could be 1,000, could be 2,000, could be the amount of points you want. Okay, and that we would like to find an interpolating polynomial. So that's the purpose of the Lagrange interpolation, to find a polynomial. Okay, so there is an explicit formula to do this. So this formula is called the Lagrange Interpolating Formula. Okay, for routing down a polynomial of degree d equal to n minus 1 that interpolates the points, we can use this formula. So we'll see that here is what I told you. So if I have 3 points, we'll see that we are going to have what? If we have 3 points, it's going to be have n minus 1. The degree of polynomial is going to be 2. Okay. So for example, suppose that we're giving 3 points. Okay. If we suppose that we're given 3 points, then the polynomial would be equal to p2, which is degree 2, is going to be equal to y1 times x minus x2 times x minus x3 divided by x1 minus x2 times x1 minus x3 plus y2, which is actually the y2 here, and then x minus x1, x minus x3 divided by x2 minus x1 times x2 minus x3, and then plus y3 times x minus x1 times x minus x2 divided by x minus x3 minus x1, x3 minus x2. So you can notice a pattern here. There is a pattern here. So if you notice the pattern, first of all, you see that always it's going to start with the y value, y1, y2, y3, right? So that will be the first thing that you will see, that you are going to always start y1, y2, y3. Okay, so then we are going to start with these all values are going to include the x's. And there in the numerator, you are going to have always x's here that are going to be actually subtracted the values of the second points or of the following points of y1. So what I mean is, for example, x1 minus x2, because you have x1, j1, so x2 and x3. So j1, x2, x3. And then because we are omitting x1, so we only have to actually see that x1 minus x2 and x1 minus x3. So this is the pattern. So if we actually analyze the second element or the second term, we see that j2, of course, if we have j2, we have to subtract x1 and x3. And if we have x2 as the element sharing the coordinate with y2, you have x2 minus x1, x2 minus x3. And the same for the last one. So if you see, it's actually a very intuitive formula. You can actually memorize it very easily because this is something that you just need to. If you have 1 point for y3, y4, for example, it would be y4 equal to y4 times x minus what? What would be the following one? If you have y4, y4 would be what? This is for 3 points. So if you have 1 more point, how would be this method? So you will have to add 1 more to these operations. So it would be x minus x4, and then here x1 minus x4, and then x minus x4, and then x2 minus x4, and then here the same thing, x minus x4, and then here x3 minus x4, and then a fourth term plus y4, x minus x1, x minus x2, x minus x3, and then on the denominator would be equal to x4 minus x1, x4 minus x3, and x4 minus minus x2, and then x4 minus x3. So we just have to modify the equation actually to do this more complex. So the Lagrange interpolation polynomial for these 3 points, if we want to do it manually, so would be as this. So the example 1 says, find the interpolating polynomial for the data points equal to 0, 1, 2, 2, and 3, 4. Okay, we already know the formula, right? So we'll see that, first of all, you'll see that 1 is here, 2 is here, 4 is here. So, and then we have x, which is equal to minus x2, x2, which is 2, minus x3, which is 3. And then you have that x1 is going to be minus x2 minus x3. And then plus 2 plus, in this case, is going to be 2. And the numerator, we're going to have actually, this one is going to be equal to x2. x2 minus x1, x2 minus x3. And then 4 divided, you will have to use x3. x3 minus x1 and x3 minus x2. And then of course we can actually make the operation. So we'll see that in general, so this is going to be x squared minus 2x, and then you will have is going to be then is going to be 3x minus 3x is going to have minus plus 6, then 2 minus 2 minus 3 is going to be 5x, and then x squared minus 5x plus 6, and then if we analyze this one, is going to be 0 minus 2, 0 minus 3 is going to be minus 2 times minus 3 is going to be positive, which is 6, right? So very simple to do so. So the same thing, we have that this is x squared, this is minus 3x, then 0 and 0. So this one. And then we'll see that you have this one 2 minus 0, and then this is going to have 2 minus 3, which is equal to 1, right? It's going to be equal to 1. And then you will have 2. 2 times 1 equal to 2, minus 2, sorry. And then it's going to be minus 2, which is a factor of minus 1/2, integrating in this formula. And then finally, we'll see the same thing for this one. So this one is x squared minus 2x is going to be 0. Then 3 times 3 is going to be 1/3. So, and then we just can actually make the operations here, multiply each of them. And then we'll obtain this polynomial, 1/2 of x squared minus 1, 2x plus 1, right? So this is the polynomial that we obtain to interpolate these 2 values. So, and then in general, P0 is going to be equal, if you evaluate this polynomial in 0, so 0, 0 is going to be equal to 1. So it's going to be equal to 1, which is the y value. If you evaluate this one in 2, so it's going to have 2 squared is going to be 4, right? Divided by 2, 2, and then 2 divided by 2 minus 1 plus 1 is going to be, well, this is going to be minus 1 plus 1. This is going to be only 1. It's going to be cancelled, and then you're going to have 2. Yes, and then P3, you're going to have 3 squared divided by 2 minus 1, 3, 3 halves plus 1, and then if you make the addition, it's going to have 3 plus 1 is going to be 4. So we have the values. So we can calibrate this. So this is the example that we obtained. So this is the explanation of how you use this example for the Lagrange interpolation formula. So the Lagrange interpolation, you can see it here. So in general, we can express this formula as this one. So in general, suppose that we are presenting endpoints. So imagine that we don't have 3, we just have several points. So for each k between 1 and n. So we define the degree of the polynomial, in this case is going to be n polynomial, by calculating an LK factor. So which one is the LK factor? Is this factor, only this. Okay, you are not accounting for y, so this is only the factor. This is what we need to calculate. Okay, so and then of course k is related to the position of the polynomial. So you'll see that if we have 4 points, we will have 4 terms here. If we have 3 points, if we have 3 points, we will have 2 terms here. If we have 4 points, we're going to have 3 multiplication. If we have 5 points, we're going to have 4 multiplications, right? So that would be the rule here. You see that is x minus x1 and then x minus xk minus 1, where k is the degree of the polynomial. For example, here, if you assume that this is going to be x minus x1, the second one is going to be x minus x2, right? And then x minus x4, well, it depends on this one, of course. If you're saying that this is equal to 3, well, let's just use the example of 4. So if k is equal to 4, so you're saying that this is going to be x equal to 1, and then it's going to be x equal to 3, x equal to 2, to 3, to 2, and then that's going to be to 3. So we're skipping this one. And the same for this one, but in this case, you're going to use all the time like x4. x4 minus x1, x4 minus x2, x4 minus x3. That's it. So that's what you're going to do in the case of the Lagrange interpolation. So once you have the Lagrange interpolation, you can actually group all the values that you need to do for the Pn minus 1 polynomials by just adding the j's values. So in this case, j1 or jn, when you have unlimited or infinite amount of n values or pair of coordinates. So this is going to be very straightforward if we actually analyze example 1 using this formula. The example 1 was P3, in this case was equal to number of points was equal, P2, this one, P2, n is equal to 3 because we have 3 points, so P is equal to 2, and then we just have J1 times L1, J2 times L2, and then J3 times L3. So which is what we have here. So this is L3. So this is what we generalize to actually do so. And then at the end, of course, if you evaluate the value, is going to be equal to JK. So that would be one of the examples. So let's do this, but you're going to do this one. So I'm going to give you the points. So find the polynomial of degree 3 or less that interpolates 0, 2, 1, 1, 2, 0, and 3, 1. 3 minus 1. So please háganlo y confirmen que da exactamente esto, de acuerdo a la fórmula que vimos aquí. Anoten los puntos. 0, 2, 1, 1, 2, 0 y 3 menos 1. ¿Ya los anotaron?
Sí, sí, sí.
Entonces, ahora sigan esta fórmula prácticamente para poder calcular el polinomio de orden. En este caso tenemos 4 puntos. Vamos a tener un polinomio de ¿qué? De tercer orden. So do you agree that this is actually correct for the first term? This is the first term. Is this correct? Or not? ¿Es correcto o no?
Sí, está correcto, profe.
¿Perdón?
Sí, está correcto.
Sí, está correcto.
Okay, so the second term would be then x1, x3, x4, and then this is going to be x2, x2, and x2. This is going to be x1. So the second term would be this one. Right? So another term could be J3, gonna be J1. Well, this is gonna be J1, 2, and 4. This is gonna be X3, X1. This is gonna be X3, X2, and this is gonna be X3, X4. So the third term would be equal to this one. So it's almost impossible to show you that right here. So that's the third term, right? And lastly, but not the least, I have 4, 4, JY4. This is going to be 2, 3, no 2. This is going to be 1, 2, and 3. This is going to be 4. This is going to be 1, 4. It's going to be 2. This is going to be 4. This is going to be 3. Oh, why is not showing this up? Just copy as PDF, maybe. And then if we go to this expression, finally in example 2, let's just open another slide. And, oh, wow. So it happens the same. So there is a limit in LaTeX. But let's just see if this works like this. I don't think so. Nope. So x2 frag is equal to this one, x4, x4, x2, x3. It's correct, but I don't know why this is not. There you go. So this is the entire solution. Is this correct?
Sí, profe, sí, sí.
So,
Sí, profe.
it's a little bit tedious because you need to do a lot of algebra.
Profe, está muteado.
Sorry. So this is going to be easy because you have in the third point, you have equal to 0. So this term is going to be equal to 0. So the only one you have to actually do is this one, these three. And many of them are actually 0 as well. So this is a little bit of algebra you have to do to corroborate that the solution is minus x plus 2. So just let me know if that's correct or not, please.
Profe, creo que he sido muteado.
So this script that I created. So in general, give me, for example, the solution.
Okay.
And this is going to be the points that actually we have. This is actually, if you think about it, so the solution is equal to 2 minus x. That's a line, right? The solution here in the presentation minus x plus 2 is actually a line. And if you check this out here in my package, so the solution is 2 minus x or x minus x plus 2. So, and the plot at the end is equal to a line. You see it here. So this is in general the 4 points that we provide. It's here. So it's a very straightforward verification, and of course, this is the result. So were you able to actually obtain this solution? ¿Sí pudieron obtenerla?
Sí.
Sí. Ahorita apenas acabo de terminar.
Okay.
Pero ok, llegamos a un polinomio menos x más 2.
Good. So continue working a little bit. I'm just gonna get some coffee. So let's then continue with something different now. So now we're moving to a new world. So in this case, as you can see, we are entering into something that we call the Newton divided differences. So the Lagrange interpolation method that we just saw, it has some inconvenience. One of them is actually that it's very exhausting in the calculations, so it requires a lot of computational work. And also when you add more numbers, more points, so it's complex because you have to repeat that again and do it again, and you cannot actually add numbers or add pair of numbers or points very easily, okay? So it's a very constructive way to write the unique interpolation polynomial, but it's not the best one, okay? This type of polynomial, the Lagrange interpolation, is seldom used for calculation because there are more alternatives and of course less tedious computationally speaking. So for those, one of the methods that is actually more efficient for interpolation, it's one method called the Newton's divided differences. Okay, this method gives a particular simple way to write the polynomial, to the interpolating polynomial. So it works as the Lagrange interpolation. So given n data points, and the results will be a polynomial of degree n minus 1. So the degree of the polynomial will not change. And the idea of divided differences is fairly simple, but some notations needs to be mastered first. So it's simple, but somehow we need to do a little bit of work or understand some of the notation. So first of all, we have to assume that the data points come from a function fx. Okay, that's one of the assumptions. So that our goal is to interpolate x, comma fx1, comma xn, comma fxn. So we see that we are assuming that the data points from a function fx. So we substitute in general the y1 and we use it as a fx1 and fxn. Okay, so this is a different notation. So in general, a formal definition very useful for the Newton divided differences is that we can denote by x1 ... xn the coefficient. This is the coefficient of the xn minus 1 term in the unique polynomial that interpolates the points. So this is the coefficient of the polynomial. In general, for example, if we have 4 points, so we're saying that if n is equal to 1, which is a constant, so this is going to be equal to 0, of course, right? So when n is equal to 2, this is equal to what? To 1. When n is equal to 3, this is equal to 2, and then when this n is equal to 4, this is equal to 3. So we're having actually denoting this value or this notation as the coefficient of the xn minus 1 of the polynomial that interpolates the points. So remember, this notation is actually the coefficient. Okay. So going there to the definition, the following somewhat remarkable alternative formula for the interpolating polynomials, as in the case of the Lagrange interpolation, we name it, if you remember, we name it Lagrange Interpolating Formula. So similarly, for Newton's method, we're using the Newton's divided difference formula. This is exactly the same. So you'll see now that this is the first coefficient, which is actually an evaluation of a constant, if you think about it. This is the second coefficient. This is the third coefficient. This is the fourth coefficient, and so on and so on and so on. So did you get what I'm saying? So this is the coefficient in general that we are obtaining from this value. So this is the first coefficient, second coefficient, third coefficient, fourth coefficient, and n coefficient. Okay, so in general, after the coefficient, we have a multiplication very similar to the Lagrange interpolation. If we have, this doesn't have a x value, this is only a constant. So for this one, we have x minus x1 for the second term. For the other, we have x minus x1 times x minus x2. And then the same thing for the others. So we just have to, multiply the second terms as in the Lagrange interpolation. Moreover, the coefficients, in this case x1 to xk, from the above definition can be recursively calculated as follows. Okay, so for example, we have the x, we have the values, right? But it's time to apply it, because if we want to calculate these fx values, so it's not that easy. So you see that the coefficient is this one, the coefficient is this one, this one, this one, and this one, right? So this is the easy part, this part. This is very easy. The complicated part is actually to obtain the coefficients, right? So the first coefficient, of course, it's just the evaluation of the formula. The second coefficient, which is equal to k, this is going to be k when k is 4, and this is when k is 1, sorry. This is going to be k 2, right? So we'll see that is x2 minus x1, well, fx2 minus fx1 divided by x2 minus x1. So when we goes to the following one, we have that this is x1, x2, x3. So we have the number calculated previously here, right? Which is in this case fx xk plus 1 xk plus 2 minus the formula calculated in this term. So divided by, in this case, the term we have in this case x1 plus 2 is going to be x3 minus x. This is x1 is going to be x3. So and so on and so on and so on. So this is the more complicated part. However, we can actually make it very simple. Simple in terms of computational speaking and simple in terms of handily speaking. Okay. If we want to use a pseudocode, so we have given these numbers, these two numbers. So we have a for loop. A for loop is just the evaluation of, from j to n, the evaluation of the coefficient fx, which is the formula. This is the formula we have, equal to jj. Sorry, to yj. So this for loop is very simple. But then we actually enter to this for loop. So this for loop is the most complicated one, because remember that this is based on these terms right here. So but it's not as complicated as follow, because we In this case, since we are just calculating the first term of the polynomial, which is a constant, so we just go to the second term all the way to n, and j goes to 1 from 1 to all the way to n plus 1 minus I. Okay, so and we have to just do the operations in general that we account in this expression. So I'll show you two ways. I'll show you the way I can actually code it and the way I'm gonna actually do it by hand. Once you know how you do it by hand, you'll see that this is piece of cake. Okay, this is the pseudocode. But let's start first by hand. So this is the Newton divided differences. So first of all, by hand, it's very simple. Use divided differences to find interpolating polynomial passing through the points 0, 1, 2, 2, and 3, 4. Okay, so this is the point. So what I do is just, manually, I just say that, okay, this is 0, 2, 3, 1, 2, 2. This is the respective point. Right? Are you listening? Are you listening to me? Yeah. ¿Sí se escucha? No, esa que está hablando loco. Okay.
Sí, profe, sí.
Okay, perfect. So we have this is just arrangement, right? So and then I have 3 columns. You know that if I have 3 points, sorry, my degree is going to be the first order. So I'm going to create a column of x's 0 to 3, 0 to 3, and a column of fx's. So f1, f2, in this case is 1 to 1 to 4. So this is what we have here. This, right? So, and then what I'm going to do is actually to follow this intersection between this one and this one, between this one and this one. So for example, the intersection here with this one is actually f2 minus f1 divided by x2 minus x1, and then equal to, of course, 2 minus 1, 2 minus x1, which is equal to 0. 2 and 0, right? So, and this 2 is equal to 2 minus 1 is equal to 1, and 2 minus 0 is 0. You have 1/2. So now we have actually this one here, 2 and 4, and then we have in general f3, which is equal to f3, because this is f3, f3 minus f4, which is equal to 2, sorry, f4, f2, which is equal to 2, and x3 here, which is equal to 3, right? And x2, which is equal to 2. So you see that now the difference for the table is actually very easy to do it, because now you have to follow just the lines. So if you have that, this is, of course, this is f1, f2, f3, right? And this is his x1, x2, x3. So you see that this one and this one, so it starts in f2 minus f1, and then x2 minus x1. And then the intersection with this one, you will have that this is equal to, of course, f3 right here, because this is f3 minus f2 divided by x3 minus x2, and this is 4 minus 2 is equal to 2, and then in this case 3 minus 2 is equal to 1, and I have 2. So this is the first degree. Okay, so and we see that this is actually what I have here: 0, 2, 3, 1, 2, 4, and then 1/2 and 2. And then lastly, for the second term, so I have, for the second degree term, so I have that this is the intersection. So the intersection is equal to this one, 2 minus 1/2, and then if you follow this, you have to follow this sequence, and you're always gonna go up. You're always gonna go up. So if you go here, so for this one, for the bottom one. So you go here, follow the line, and you get 3. And then here, follow the line, and you get 0. Remember that this is equal to the y's, and this is equal to the x's. So you just have to follow the line, you get 0. You got follow the line, you get 3. And because this is always 3 minus 0, this is always the upper minus the lower. So you get that 2 minus half, in this case, is going to be equal to 3 halves, and 3 minus 0 is equal to 3. And then cancel out, and this is going to be equal to 1 half. So the terms that we are going to use for the polynomial is 1, 1 half, and 1 half. And so we have to use these terms 1, 1 half, 1 half, because this is the first, well, this is the constant first and second term. Then if we follow the notation that we see here, this is piece of cake now. So I see that the first term is equal to x1 is equal to 1 because it's equal to 1 here. The second term is equal to 1 half equal to 1 half. And then you follow what you see here. Sorry, what you see here. So this one is x minus x1. How much is x1? 0. X minus x1, 1 half, and then 1 half, which is this term, the third one, and then you have that x minus x1, 0, and then x minus x2 is equal to 2 here. And making math, this is 1, this one is 1 half. This, of course, this is equal to x squared minus 2x. This is going to be 0, 0, and then so is going to be x squared minus 2x, 1 half. And then multiplying this one is going to be this one times this one, 1 half x squared, and this is going to be x minus x actually, and this is going to be 1 half. So just arranging the numbers, you know that you have this 1 half x squared. This is negative, so 1 half minus 1 is going to be minus 1 half of x and plus 1, which is this one. So you see that following this notation is actually easier. So making this actually in a table would be easier. If you do this in Excel, it would be easier because you don't have to get complicated with, oh, what I have to do here with all these crappy things, right? So it's making this in a table in Excel is better than just being, you know, crazy and trying to solve all the work by yourself. So let's just do one more example. But in this example, it actually says that add the fourth point 1, 0 to the list in example 3. So we have all the points, but we are adding 1 and 0. So we are adding 1 and 0. And here you're going to see actually the advantage of the Newton divided differences. So the first that all the work that you did here, 1, 2, 4, it's saved here, right? 1 and 2, 1 half and 2, 1 half and 2. It's saved. And then you do the same, and then 1 half, 1 half. So it is saved, right? So you don't have to actually be worried about, you know, if you add one more number, what you have to do, just put it down here on the table. And then we tell like, OK, let's just do this one. So you know that this is f4 minus f3, and then divided by x4 minus x3. So how much is x4? 0. How much is f3? Minus 4. So it's going to be negative. So and then how much is actually x4? 1. How much is x3? 3. 1 minus 3. And then this is negative 4 minus 3 minus 4 minus 2 is going to be 2. And then you have to do the same thing using what you already had in the previous example. OK, so in the previous example, then you have these two. You have to just do what you have to do. 2 minus 2, and then the same thing. You follow the line. Check it out. Check how you follow the line. Follow the line. Follow the line. 1. And then follow the line. Follow the line. 2. So you just have to follow the line. 2. So 2 minus 2, 0. 1 minus 2, 0. And then you do the final and third term, which is actually 0 minus this one, and then 1 and 0. So how you do this? Follow the line again, follow the line again, follow the line, you get 1. Follow the line again, follow the line again, follow the line again, you get 0. 1/2 divided by 1 is equal to minus 1/2. So the terms that I want to use is equal to 1, 1/2, 1/2, and minus 1/2. So, and I got this one, 1/2, 1/2, 1/2, and minus 1/2. Same thing. So what I'm doing is just actually substituting this, what I had here already. This already had it, remember. So, and then I just substitute the minus 1/2. This is equal to x minus, this is x 1, which is equal to 0, 2, and 3. 0, 2, and 3, right? 0, 2, and 3. And then you just have to do the numbers, do the math here. You can actually, you know that this is actually the polynomial that we already had. This polynomial px. This entire thing is actually p2x, so we don't need to worry about this one. So then I just have to do the multiplication of this one. So if you do it, so you'll see that it's going to be, first of all, x squared and minus 2x. Then the other two are 0 times x minus 3. This is going to be, and then you multiply this one times this one is going to be cubic x minus 1/2 because you have a constant here. Multiply this one again. So this is going to be x squared, 3/2, of course, because it's below here. And then this one times this one is going to be minus 2x squared. And finally, 2x minus 2x times minus 3 is going to be 6x. With this value here, we just multiply or substitute p2x, this one. And then we substitute this one in the parentheses. So and at the end, we obtain this value. So this is how we get it. So this is the way we do it. And then I'm going to show you how to actually code it. I just coded. I coded in MATLAB as well. So Newton divided differences. Here you have the Newton divided differences. For example, I'm going to create the example here. Let's do both examples. So if I do both examples, so you know that x0 is equal to, well, actually, I'm going to do it like this. You see that x is equal to 0, 2, 3, 0, 2, 3. Evaluate selection. It's already here. Give me a second. It's already here. So the other one is 1 to 4. 1 to 4. 1 to 4. Okay. And then I apply the Newton divided differences model that I already did. It's here. You see that this is actually the first for loop and the second for loop. It's here. And then I use the way to evaluate the values. So I just gonna do the Newton method here. So it's gonna be, you see 1, 1/2, 1/2. So the C is the vector that I have in the solution. In the here, 1/2, 1/2, 1/2 minus 1/2. No, this is another one. Sorry. This is the one here. 1/2, 1, 1/2, 1/2. So if you see here is 1, 1/2, 1/2. And then I want to evaluate the value. So I evaluate the value. I create a range of x. I'm using the nest. If you remember the nest that I created, the nest formula. And finally, I'm going to plot my function. So here you have the function. So you have 1, 2, 3 points, and then the line that we just created. This line is equal to this polynomial. And then let's just do the following one. So let's just do the following one, which is this one. So, and this just consisted of adding a new point. So this is just piece of cake because we're just adding 1 and 0. So I'm gonna just do this. Evaluate. I'm gonna evaluate this one. I'm gonna make a, this is what this is for. Evaluate. So 1, 1/2, 1/2, minus 1/2. This is the values that are obtained here, right? Remember? So minus 1/2 was the one I added. So I'm gonna create the space again. Well, you'll see if this is the same space. I'm assuming that it is. So, and this is gonna be a 3rd-degree polygon. Right here, and then the plot finally is going to be this one. So you see that 1, 2, 3 points, and then we have another shape right here. So it's exactly the same thing, and then you have the solution that we obtained here. So this is the polynomial. So we see now 3 examples. One well, 2 examples of Newton divided differences. So I'm going to ask you to do it, but this is going to be for the exercises. So because we already have 1 hour and a half, so the video is going to be cut off. So you're going to do for tomorrow, no, for Thursday, you are going to do this one. So I already give you the solution, and for the assignment, you're going to do this one. Okay, this is for the assignment. Okay, this is for practicing. You're gonna do it and you're gonna tell me if you have any problem, any doubt. You have this one. Oh, I think we already did this one, which is actually the same thing that we did with the Lagrange interpolation. This one, I think it was the same thing. So let me see. Yeah, it's the same one. So it's the same thing, right? But we just want to verify that it's by the Lagrange interpolation. We obtain that this is 2 minus 1, 0, 0, and then we substitute it, and then you have 2 and minus 1, which is equal to this one, and you have 2 minus x. So it's not very difficult. You will able to do it. So this is not an assignment. This is just for you to practice and to verify that the Lagrange and the Newton divided difference are exactly the same. So you're gonna do it, and you have the exercises. But these exercises are not on. Estos ejercicios no son una sola tarea. Estos se van a juntar con los splines, con la tarea de los splines, que vamos a ver el último método de interpolación el día jueves. Lo vamos a ver. Entonces, para que sepan que estamos viéndolo. Por ahí creo que les voy a dar un vídeo el día jueves para los splines, porque no estoy seguro, porque tengo una junta, creo, con la academia. Entonces, por ahí a lo mejor reciben un video en lugar de mi atención. Okay. So, do you have any more questions? Do you have questions? Sorry.
No, profe.
No. Either way, if you want to review the class, remember that all the classes are here in Teams or in my YouTube channel. Okay. So you were able to actually watch it. Okie dokie.
Okay, profe.
So that's it for today, guys, because it's 11:30. So if I continue, I'm gonna split the videos in 2, and I don't like that. So keep practicing. Try to do. Háganlo en la última media hora. Hagan y por favor reporten si les da. En el grupo de WhatsApp, ahí estaré yo también. Reporten y nos vemos la siguiente clase el día jueves. Ok. Que tengan un excelente día y peace out.
Igualmente, profe, cuídese.
Thank you very much. Bye-bye, guys.
Nos vemos.
Bye-bye, Juan Manuel. Bye-bye.
Hasta luego.
Bye, Esperanza.